So now we move to testing for proportion. First and first, summations. N for sample size, P hat for sample proportion, P for population proportion, P naught proportion under the null hypothesis H naught, and Z for standard normal distribution. And we also consider three type problem, testing proportion for two tail, right tail, and left tail. So two tail, which is P equal P naught versus P different P naught. The right tail, P equal P naught versus P greater than P naught. The left tail, P equal P naught versus P less than P naught. So we have a theorem 931 here. It tells us basically like how you can calculate test statistic and what distribution it follow. So say if you test for proportion, it can be two tail, right tail, or left tail. And the test statistic calculated by using P hat subtract P naught divided by square root P naught 1 times P naught divided by N. Here P hat is a sample proportion and sample size and P naught is the value under the H naught, the null hypothesis. And it can be shown that your test statistic will follow a standard normal distribution. And the requirement we want to make sure we can use a theorem is that like we will require simple random sample procedure. We require sample size less than 5% population size. We require the sample data can be classified either to success or failure. And in order to get a good approximation, we also want that the n times p naught 1 times p naught 1 subtract p naught greater than or equal to 10. So this is some condition you need to check, right? Do a sanitize check before you apply the theorem. So given that with the critical value method, okay, your rejection region for the right tail test will be T greater than Z 1 minus alpha. For left tail will be T less than Z alpha. And the two tail will be either less than Z alpha by 2 or greater than Z1 alpha by 2. And Z1 alpha here is just the inverse norm, right, of 1 alpha 0, 1. This guy is just the inverse norm of alpha 0, 1, and the same thing here, right? The inverse norm of alpha by 2, 0, 1, and inverse norm of 1 alpha by 2, 0, 1. So this is how you make decision. It depends on the test, right? So you can see that instead of previously we look at a T, right? Now we look at a Z. And for the p-value method, and then this is how you calculate p-value method. For right tail test, property of Z greater than or equal than T, which is it's just basically a normal CDF, right? T, a big number, and then 0, 1. And for the left tail test, will be property of Z less than or equal than T, just normal CDF, a very small number to T and 0, 1. And a two tail, again, it's just like 2 times normal CDF of absolute T, a big number, and 0, 1. So it just translates everything back to kind of a similar fashion we probably see in a T distribution. But now you don't look at the T distribution in degree freedom, but you look at the normal, standard normal. Okay. So let us walk through some examples, and you can see how we're going to perform a test for proportion. So a cell phone possession. A common belief is 90% of adults on cell phone. A startup cell phone company think that the actual number is different with 92%. So they talk about different, right? Percent, which is talk about proportion here. And we talk about different, right? Different. So they conduct a survey of 200 adults and found that 174 having cell phones. Set up a testing problem for the startup company and say the conclusion, okay. So we help them to set up testing problem and use the data they collected to make a decision, right? Then identify type 1, type 2 error. So let's see. So this is the testing for proportion, right? Proportion. So a good practice is that you need to check the requirement, right? So your requirement 4-star here, I think 4-star here, right? So you check it, all right? See, okay, sample, random sample, the sample, right? Random 5% population size, less than, right? It must be, right? Because 200 people, we have millions of people have cell phone, right? Data people, successful people have cell phone or not, right? N P naught 1 have subtract P naught greater than or equal to 10. So in this case, P naught would be 0.92. If you can plug in, right, you should be able to see that like 200 times 0.92 and times 0.08. Let's see whether I get it, which is N, right? 10.92 value under the null, 10.08, which is 1 subtract 0.92, right? So which means we get a good approximation here, but theorem perform well. So we check and requirement satisfy, and we state the testing problem, right? Because here we care about percent and proportion, and they say they believe that, right? It's different, right? So it's just P different 0.92, and this here is not. So these are two test problem. And from that, say if we look at the critical value method, and basically you need to look at this 932 here, right? And then your T will be P has subtract P naught divided by this square root, right? P naught 1, P naught divided by N. So here your P naught will be 0.92 value under the null. P hat, which is the proportion, sample proportion, right? Which is 174 divided by 200. N is 200. And here we want the alpha is 5%, alpha 5%. So given all those, you can find out that the test statistic is negative 2606. You plug in. And with the critical value method, what you need to find is that the Z, because you do two tail, right? Z alpha by 2 and Z1 alpha by 2. So Z alpha by 2 is just the inward norm of alpha by 201, and in this case it will be 0.025 because we talk alpha 5%, right? So you plug in your calculator, you should get a negative 0.96 here. And this guy 1.96, inward norm of 0.97501. You can also use symmetric property, right? You just flip up this guy into the side. The side, right? So basically, in this case, you see that whether you can reject or not, it really depends on your test statistic to the rejection region here, right? And obviously, you can see that 2606 here is much less than 196, right? So which means you reject the H naught B equal 0.92 and support the alternative at this significant level. And then the second question is identify type 1 error. So here in this type 1 error is the error happen when you reject a notch, right? When you know it's true, right? Which is you reject P equal 0.92, but when it's true, right? Which means in fact it's true, but you reject it, right? So here, like also the same problem when we look at like maybe different hypotheses you want to test. So just everything the same, but now some maybe another startup, right? They think like people have cell phone greater than 92%. And maybe another company say, oh, it must be less than 92%. Okay. So how about that? So given that the first case, it would be right tail test, right? Because they believe in bigger than, right? And for the second case, it would be left tail test because they believe less than. But it doesn't matter what they do, the test will be the same, just a negative 2606. But the only thing changed will be the decision, okay? So because it's a right tail test, so you basically just look at here, right? To see whether, you can get this, right? T greater than Z1 alpha or not, right? If it's yes, then you can reject. If no, you cannot. So for this case, you can see that your Z1 alpha will be 1645, and you don't have that luxury, right? You don't have your test statistic bigger than Z1 alpha here. So which means you cannot reject, right? H naught, right? At significant level at 5%. Let's say if you test this same way, and basically your decision for the left tail test will be T less than Z alpha, right? For left tail here. And which means in this case, your Z alpha will be negative 1645. So which means you can reject, right? You can reject. So you see, like from the same data, right? For different testing problem, you have different conclusion. Example 933, child care responsibility. Here, like an article journal, it reported that 34% American father take no responsibility for child care. And a researcher, he claimed that that percentage at the time Littleton is higher. And then he collect a sample up to 34 further at the tail, and he find out that 96 did not have a check here. In part A, the researcher claimed a significant level 0.03 using the p-value method. And in part B, what decision when using the critical value method? So now you can use the method alternate, right? Either p-value or critical value. But it doesn't matter what method you use, right? The conclusion should be consistent. But here we just want to check whether that's the case here, right? So first thing first, check requirement, right? For star here, you can plug in and see, if it met, right? It's a good practice, right? Good practice. So first, sample random sample size less than 5% population size. Sample data either success failure, right? Take care, not take care, and NP not 1 minute P not greater equal to 10. You can plug in your calculator and all the conditions should met, right? Before you process things forward. So here, you see that with that, right? You set up the testing problem because the researcher here, he believed that the number is higher, right? And here we talk about percent. So which means we talk about proportion. So yeah, the alternative up here, the researcher will be P greater than 0.34 versus the no with P equal 0.34. And because in part A, we look at the p-value method. So we look at the theorem 93 here, right? In order to do p-value method, first, you need to calculate test statistic. And then with right-tail test, this is the p-value you calculate for right-tail test. So here, the test statistic will be B in here, subtract B naught, divided by this quantity. So you plug in here, your B head, here. You plug in here, your B head will be 0.41, subtract 0.34, and divide by this much. So be very careful with the numerator, okay, the quantity. So I would suggest if you will do a manual calculation, just, calculate the denominator first and then plug it. Don't plug the whole, often it will cause a consequence. You may mess up something and it should not give you the right test statistic. So this case, you plug in and you should be able to get a 262 here, 2.26. And the p-value for the right-tail test would be probably z greater than 2.26 here. So basically, it's just a normal CDF, 2.26 to a big number, 0.1 here. And if you plug in, you get this 0.012. 0.012, I think it's a typo here. And since the p-value 0.012 here, so it's less than 0.03. So in this case, you reject the H naught and support the HA. So basically, you can support the researcher claim as in level 3%. And say if we want to use the critical value methods, and then we have to stick with theorem 93332 here. So for a right-tail test, the test statistic will be the same, right? But the decision will be you can reject if your t greater than z1 by alpha. So in this case, your z1 by alpha will be z1 by alpha will be z.97, right? z.97. And it's just the inward norm of 0.9701, and it gives you 181 here. So let's do it together. Inward norm, right? Second, inward norm here, 0.97. 0.88, right? 0.81. You keep 3. So given that, you can see that your test statistic here is bigger than the cutoff, right? So which means you reject the A naught. So here, again, you see the conclusion is the same for both methods. Again, both methods. So it doesn't matter p-value or critical. The conclusion will be consistent and consistent. Let's look at this quiz together. So assume that alpha 0.05, so it's a significant level of 0.05. Claim we made that the mean number of in a batch, right, blue M&M is greater than 2%. Okay. So I think like I just copy exactly what one of the previous tests, okay, contain. Yeah, but I think the marker would be say the proportion of percentage blue M&M, right, is greater than 2%. And the hypothesis test the result that p value is of 0.0451 and choose the correct conclusion. So here, like, it doesn't matter what the problem is, as long as you have the significant level and you have the p-value, you should be able to make a conclusion. So don't be confused by the content too much, okay? But here, like, let's look at what the p-value you have here for the test and what the significant level, right? So significant level 0.05 and the p-value 0.04151. So the way we make a decision with p-value method is that we look at whether the p-value less than significant level or not. So in this case, the p-value 0.0451 is less than significant level 0.05. And it should be enough for us to reject the null, right? So basically, it will be A, reject the null since the p-value less than significant level. So don't be confused by these things, right? And also the logic here not right, right? 0.0415 less than 0.02 here, right? And here good, but this one wrong, right? When the p-value less than significant, the significant level, and then you reject. So which is the choice will be A. So now let us look at the child care responsibility example, and again, but now we're looking from different perspective. So the same problem, the same data, but John, he believed that in little town it's better, right? So the percentage of father who take no responsibility in child care in the town here is less than 34%. But Mary, she think she doesn't have any specific preference, so she say it's different with 34%. So because their claims are different, right? So basically, like the test setting will also different, and the conclusion will be different. So for John, because he say it less than, so he will need to test for the hypothesis P less than 0.34. And because that, the p-value he need to obtain will be probability of Z less than 2.6, okay? So you should be aware that it doesn't matter you do two-tail, right-tail, test-tail, the p-value will say stick at the same. The t-test will stick the same, which is p has subtract p naught and divided by square root p naught 1 times p naught by divided by n. So it always 2 to 6 here. It doesn't matter what test you're doing, as long as the value under the node stick, right, at the same level. So here, like in this case, the p-value will be, because we work with the left tail test, right? So p-value for John case will be probability of Z less than T, right? So this is a left tail test here. So which means it will be Z less than 2 to 6, right? And again, the equal sign here doesn't matter, right, for the continuous data. So if you normal CDF 999, 226, and you get a 988. And which means that this p-value must bigger than 0.03, right? So you cannot reject the null. And this is one level. In order to reject a null, you need the p-value less than significance level. And for Mary, she worked with two-tail test, right? So the p-value for her case will be probability Z absolute greater than equal than T absolute here. And we can translate it back to like 2 times P of Z greater than 226 here. Just 2 times normal CDF 226 99901. And it gives you this much. And for this much, right, it's less than a p-value, the significant level 0.03. So for her claim, she still can reject a null at significant level 0.03. So her claim is supported by the data, right? And the good news is that you can also use the point proportionality test function to perform a test. So in the case you use p-value method, and it will also give you the p-value. It will give you the tested value, but when you use the critical value method, you need to specify what the critical cutoff, right? But if you use the p-value method, you should be fine, because for a testing problem, they always give you a pre-specified significant level. So all you need to do is that you just need to compare the p-value extracted from the calculator with the signal level provided to make a decision. And you need to insert the n, the sample size, the p naught, the value, the proportion under the null. The x is the success, number of success, which is the event you care, right? So furthermore, the event you care about, the child care and little tail, a success here, which means you can find a father did not take responsibility of child care, right? And the n is I think here we have a redundant here. And it depends on the two tail, right tail or left tail, you with the corresponding choice, right? And one note here is sometimes, your data, you don't have the X, which is number success. And other time you need to process a little bit by rounding using N times P hat and round it to the nearest to get the X, okay? So now let us look at the check little tail, right? For the 933 problem. I think 932, right? 92, 93 here, okay. Okay, 93, right? So which means you test for greater than, right? Researcher, he believes that it's greater than, right? So this is a testing problem in 933. So we just rewrite everything here, but now instead of we do manual calculation like we did before, we will plug in a TI calculator, okay? Testing by H naught be 0.34 versus HA be greater than 0.34. And here your sample size, here your P naught, and here your X, right? 96 here. And we work with right tail, right? So let's do it together. So you do a start here, test, and choose one process test here. You have 4, 3, 3, 4, right? P naught, value under the null. Here you do the right? So you give us like 2 to 6, right? 2 to 6, 8. You give 3, right? 2 to 8 and 0.012, right? You give the 3, right? Give 3. 2 to 6, 9 actually. You give 3. And upon 0.12, right? It's 0.012. And p hat, which is sample portion here and sample size here. But anyway, I think it's consistent with what we get here, right? And the p-value here. And here, like, if you look at the p-value method for the the 933, right? Because in 933, we have 2 questions, right? Use the p-value method first and use the critical value, right? So when you use p-value method, your life is easy, right? Because your calculator already give you this, right? 0.012, right? 0.12. And all you need to do is just compare with the significant level 0.03 here. And for here, you can see that your p-value less than significant level. So which means you reject the H naught and support AA. And if you plan to use a critical value method, and then one additional step you need to do is that you need to find out what the critical value, right? So for this test, again, the critical is 1AA1, and you compare the test statistic 2 to 6 here, right? 2 to 6, 9, if you keep 3, and we say that we reject, right? But either way, the conclusion is still consistent, right? It must be consistent. So here, basically, here just the squeeze, just the testing problem, the whole we need to work on to see, step by step, right? So an article in a journal report, okay, so we just keep repeating the little town example, right, about child care, okay? But now we look at it in a more comprehensive way, which is the whole procedure, right? An article in a journal report that 34% of American fathers take no responsibility for child care. Research claimed the figure higher, right, at the town Littleton, okay, which means it's higher, right? The percentage higher. A random sample to 34 fathers from Littleton yield 96 did not have child care. That research claim at significant level 0.05. Answer the following. So now you just need to fill in the blank. What is a claim? What is no hypothesis? Alternative? What tested it, right? Shade it, rejection, and then just follow exactly what is asked, right? So what's the claim here? The claim here is that like that, right? The figure is higher for Littleton, right? Littleton. So if you want to make it more specific, we say that the claim here, like the percentage, the proportion of father at Littleton, right? not take care, not take a responsibility for childcare is higher than 34%. Right? So at time with that claim, and then basically you can write out the no, it will be P equal 0.34, right? And alternative P greater than 0.34. So H naught would be P equal 0.34, just like exactly what we got in 93, example 93. And our alternative would be P greater than 0.34. In the test statistic, just exactly what you got before, right? P has subtract P naught divided by square P naught 1 minus P naught divided by N. And you plug in and you should get the value of 2.26, right? If you keep 3 will be 2.269. And I shaded the rejection region, so this is a new thing, right? So this case, because we work with a right tail test problem, okay? So the rejection region will be the right tail, okay? So it'd be like this. You can shade that. What the p-value? Just exactly what we calculate here, right? P-value will be 0.12, right? 0.12. Can we reject the null hypothesis? And again, here, you compare the p-value 0.012 with significant level, right? And obviously, your p-value is less than significant level, right? So we can reject hypothesis, right? And the last one, write complete sentence addressing the conclusion about the original claim. So the complete sentence is that like based on the sample data, right? We can reject the null hypothesis at significant level 5%, right? You can also write maybe based on the sample data suggests that, right? There are enough evidence to support the claim of the proportion of father at a time little turn not supposed for child, not take responsibility for child care is higher than 34% at a significant level 5%, right? So it's very important when you make conclusion. There are two things people look at: whether you reject the H naught or not, right? You can support your claim or not, and what significant level, right? And as you see in one of the previous example, right? If you increase your significant level to a certain number, right, you can always reject, but sometimes it will be meaningless, right? And people won't buy it, right? And we want to keep the significant level as a low side, maybe 0.05 as a universal starting point. You can make it more stringent, 0.01. Maybe sometimes you increase a little bit, say 0.08, 0.1, or even 0.2, but you don't want to go higher, right? So say like here, we just consider one case where, what if one of the condition violated, right? For a simple random condition, often, it will meet because, when you collect data, you have to think about that, right? You need to make sure your data reflects the population. For the second condition, which is the sample size less than 5% of the population size, often a lot of cases it also meet, right? Meet because we want to make sure it won't be affected when you draw without replacement. The condition of successful also emit, right? People will either have a property or not have property. But the condition mostly violated will be this condition, n times p naught 1 minus p naught greater than equal to 10. We need this condition because we want it to get a good approximation for the theorem. Okay, so there's some math behind. But basically, like, what happens if this condition violated? Another time you cannot perform the test like you typically do. Okay, but we use binomial distribution in chapter 4 to perform that. So we will have a theorem to give you the decision, okay? So if the condition n p naught 1 p naught greater than equal to 10 violated, okay? And then basically like you can use the p-value method and reject the h naught if your p-value less than alpha, and your p-value calculated in the way probably x greater than or equal than x. Yeah, x is just the number of success among n trial, among your ensemble, okay? And x is the number of success, right? So x is just a distribution of number of success among n trial, and small x is number of success collected from your data. So if you consider right tail test, this is your p-value calculated. Even left tail test is p-value calculated, and this is for two-tailed test. Okay. So let's look at the example, so you can get a better sense about how we can process things forward when the condition violated. So in 2006, 10.5% of all live births in US were to mother under 20-year-old. A sociologist claimed that the births to mother under 22-year-olds decreased. Okay, so he or she say that it decreased now. And we talk about percentage and proportion. Right? And then the sociologist random sample 34 birds and find that 3 of them were to mother under 20-year-old. That's a claim at the signal level L5.01. So here, like for a careful person, right, they will verify the condition for star, right? So you can see that like you have some, let's look at 4 star together again. So you see what may fail, right? So sample random sample is correct. Sample size less than 5% for sure, because you have a 34 mother, right? 34 birth, so which means much less than 5% of 100,000 births we have each year, right? And here, like, what else? The condition here is asked. Sample either success or failure, right? So people maybe, so basically here they also satisfied because birth may belong to mom under 20-year-old or not, right? But this is the guy you need to take extra care, right? So if you look at this guy, yeah, test environment will be basically like so first maybe I will set up a testing problem. Okay, then we'll check condition. So the HA you want to test here will be P less than, right, 0.105, because the sociologist he think that the birth due to mom done under 20 decrease, right, and decrease compared to benchmark of 10.5%, right? So this is the claim he or she wants to support, right? And the value under the node will be 0.05 here. So when you do that, you see, you check the condition here, you see 34 times this much, and it will be less than 10. And which is the condition violated, and which it not allow you to use the theorem, right? Because the approximation will be not good. Not good. So what we do, we will use the theorem 934 here in this case. You're not allowed, and you should not use the normal approximation way with 932 or 933 to make the decision, right? So in this case, what we do is that because we work with the right tail test, right? I'm sorry, the left tail test problem. And we just follow this track, right? So here, like the number of births due to the 20-year-old and younger mom will follow a binom of n, which is 34 and 0.105, right? So at this time, you usually know the number of mother less than 20-year-old. Among 34 mothers, so X will be modeled by this. And because we're testing this problem, so we look at the p-value for left test, okay? The left test problem. So this become X less than equal to 3. So now I just return to a binom CDF function very easily. Binom CDF NP, right? 34.105 and X. And in this case, you get the p-value, which is 5.149. And then to make a decision, you compare the p-value with significant level, right? And significant level we want here is 0.01. So you can see that it's greater than 0.01. So in this case, you fail to reject A not as significant level 0.01. So this example is just we can bring here to bring you the attention. Sometimes, the requirement fail. And at the point it failed, you need to find other alternative. So it's always a good practice, to check the condition before the process forward with the theorem. Okay. But I think unlikely we will have this kind of problem in the test. But here, just want to bring you to the awareness of what if the condition fail. So thank you so much for your attention, and I'll see you in chapter 10.